All right, back again, and now we're going to do problem 2 of this problem set. And in this set, you're giving a series of powers of spectacle lenses at a given vertex distance, and they want you to find out what the appropriate contact lens correction would be for this patient. Right? They want you to draw diagrams, show effectivities, changes, and then they want you to use the effectivity formula. All right, so we know there are 2 ways of completing these problems. We're going to do both, and we want to make sure that our 2 answers equate to each other. All right, so for the first problem, I have a pair of spectacle lenses. They are a +4 and is given to you at a vertex distance of 15 millimeters. All right, so I have a diagram that looks something like this. I have a pair of positive spectacles of a +4. I have an eye that's located here, and then it's given that the distance from the spectacles to the eye is 15 millimeters from here to here. And what you're doing is you're sliding this lens towards the eye so that it's actually in contact with the eye, right? And then they want to know what the power is right here. All right, so 2 ways of doing it. The first way we're going to doing is by the focal points, okay? So what I have is a lens that is a +4, all right? And then that lens, we're assuming that we're having parallel light entering it, because that is what this correction is for, to see at a distance of optical infinity. So parallel light coming in is going to cause that light to converge, and that light will converge to the right of the lens, and we're going to call this the focal point of the lens. Right? And that focal point of that lens should correlate to the far point of the patient's eye. This individual with a +4 correction is obviously a hyperope, and you should know by now that the far point of a hyperope is going to be behind the plane of the retina or somewhere inside their skull. All right. Now, just before we even start, we want to know, what is the answer to this going to be? Is a contact lens correction of this gentleman going to be more or less than 4 diopters in magnitude? All right, so what we're doing is we're taking this correction here and we're sliding it towards the eye. I'm sliding it in this direction here, to the right. This is the path of light coming in this way. All right, this lens is going to create a converging wavefront. I'm going from an area here to an area here. All right. The magnitude of the converging wavefront is going to be greater, closest to its focal point. So I know that this correction here, and our analogy is going to be the contact lens, needs to handle a higher level or higher magnitude of converging light. Therefore, the power or the magnitude of this contact lens correction has to be greater than 4. All right, so that's simple. We already know that the answer has to be greater than 4. When we do our calculations, if the answer comes out to be an answer less than 4, we know that answer is inherently wrong. Okay, and we have to double check our work. The easiest place you would make a mistake is doing your calculations. All right, so always have a way of double checking yourself. All right, so I have a 4 diopter lens. Okay, I need to know where this focal point is located. And that focal point, and this is a dioptric value. I want to convert it into a linear value, so I'm going to take its inverse. All right, take the inverse of 4, and that gives you 25 centimeters. So it's 25 centimeters from here to here. All right. This is where the contact lens is going to be lying, and I want the wavefront coming out of the contact lens to form a focal point at that same point. All right, and so the focal distance of the contact lens is going to be from here to here. And this is the value that I have to know. How am I going to figure that out? Well, I know from here to here is 25, and this slide here, the distance from here to here, is the vertex distance. All right, so it's 15 millimeters from here to here. So to find this guy, I'm merely going to take the focal distance, 25 centimeters, and then I'm going to subtract the 15 millimeter vertex distance. All right, this is going to give me a 5, that leaves me a 4, that's a 3, and that gives me a 2. So this value right here, between here and here, is going to be 23.5 centimeters. That is the focal distance of our contact lens. Contact lens, I need to have that in a dioptric value, so I'm just going to take the inverse of that focal distance. And when you do that math, it's going to come out to be 426. And this is going to be the power of our contact lens. Contact lens is going to be a 426. 426 is greater than 4. Right? So we get half a shot of that being the answer. All right, what's the second way of doing it? Well, the second way of doing it is using our effectivity formula, or the formula we derive from our basic Gaussian formula. And we're looking for the power of the contacts, all right? And where I'm going to get that from is the power of the specs. And the difference between the two is this ratio here, 1 minus the vertex distance times the power of the spectacle correction. And so in this case, the spectacle correction is going to be a +4. 1 minus the vertex distance given to us in the problem is 15 millimeters. Now I'm moving from here to here. I'm moving with the path of light. Therefore, the sign of the vertex is going to be positive. And then the power of the specs, once again, is a +4. All right, so this is a positive value times a positive value. So this is 1 minus a positive value, which means that this denominator is going to be a number less than 1. If this is a number less than 1, this overall value here is going to be a value greater than 4. Now that makes sense. Another way of double checking your sign. And when you do the math for this, you're going to find that the answer is exactly the same, 426. All right, so I can do the problem through the Gaussian formula. I can do it through the focal lengths. The answers are going to come out to be the same. All right, easy enough. So that was for the 4 diopter value. We're going to do that again for our next scenario. And the next scenario is given to you as a positive 8 diopter lens. And the vertex given for that problem is 18 millimeters. So I'm going to have some sort of positive correction here. In this case, it has a value of 8. Here is my eye, and the distance from the plane of the eye to the plane of the spectacles is 18 millimeters. That's my vertex distance. Okay? And then what I want to do is place a lens at the plane of the eye. The vertex distance will be 0, and I want to know what that's going to be. Well, just like our original problem, this is going to create a converging wavefront. I'm actually going deeper into that converging wavefront. So I know that the value of this contact lens has to be a value greater than 8. Okay, no different than the previous 4. All right, so once again, I'm going to take my original lens. That's going to be my +8 for the spectacle lens. It's going to create a converging wavefront that's going to have some sort of focal point. The assumption of the problem, if that is the patient's correction, that focal point is going to be incident with the far point of the patient's eye. Hyperopes, far point of the patient's eye should be behind the plane of the retina or on this side, so that makes sense. Now I want to know what the distance is from here to here, the focal distance of that lens. To do that, I'll take the inverse of the power of the lens. Once again, the 1 is because the lens is outside the eye, and we're assuming that the lenses, the contact lens and the spectacle lens, are in air. In other words, your patient is not in a swimming pool, and so the index of refraction of air is 1. That's where the 1 comes from. Take the inverse of your 8 diopters, and that gives you 12.5 centimeters. So the distance between here is 12.5 centimeters from here to here. I'm not going to take that correction. I'm going to slide it this way towards the eye. Okay, this is now the contact lens, and I want to know what the power is there. This is the spectacle lens over here, and this is my contact lens over here. This, for this contact lens to work, to equate to this system, the focal point created by the contact lens must be coincident to this same focal point. So I need to know what the distance is from here to here. This is actually the value that I'm looking for. And then once again, to find that, I know that the amount, or the distance rather, of slide from the spectacles to the contact lens is given to, and the problem is the vertex distance, which is 18 millimeters. So I know the distance from here to here is 18 millimeters. To find this, I'll take this and subtract this. So I'm going to take my 0.125, and I'm going to, excuse me, I'm going to subtract my 0.018, and when I do that, that gives me a value of 0.107. And so that is the value here, 107. So 10.7 centimeters from the plane of the contact lens to its focal point. That's the linear value of the focal distance. I'm going to take its inverse to convert that into a dioptric power. And when I do that, that comes out to be 9.35 diopters. All right, and that's going to be a positive value. That is the value of my contact lens. All right, that is the focal point way. We're going to do it once again by the Gaussian way, or the effectivity formula. I'm looking for the power of the contact lens. I'm going to take the original spectacle correction, which is a +8. I'm going to divide it by 1 times the vertex, 1 minus, the vertex distance, which is 18 millimeters, times the power of the spectacle lens to start. And then once again, I'm moving from here, from spectacles to contacts. I'm going in the path of light, or with the path of light. Therefore, the vertex has a positive sign associated with it. All right, so plus times a plus gives me a plus. Once again, my denominator will be less than 1, so my overall answer is going to be a number greater than 8. 9.35 greater than 8. Everybody is happy. Do the math for that, and magically, it comes out to be 935. All right, there's the value there, and there's the value of your contacts there. Once again, there's just 2 ways of getting there. In this case, you're equating focal points. In this case, you're equating the equivalent powers of the 2 systems. This would be the one system, the system of the contact lenses. This would be the second system, the system of the spectacle lenses. Okay, in this case, you're equating the focal point of the contacts to the focal point of the spectacle lenses, and both of those must be equal to each other for those corrections to be correct for your patient, and that's why these 2 values remain the same. All right, so that was for a hyperopic correction. We're going to do it again the next set of problems, or 2, not next set of problems, but the 2 remaining parts of problem 2 are going to be for a myopic correction. So in this case, it's a -7 pair of spectacles, and they're worn at a vertex distance of 12 millimeters. So in this case, I now have a minus lens that's placed in front of the eye, and the distance from the plane of the eye to the plane of the spectacles is 12 millimeters. That's the vertex distance. Okay. Once again, the path of light is going in this direction. All right. So I now have a lens that is out here. It's a minus lens. I'm having parallel light coming into that lens, right? Correction is for distance or optical infinity. All right, but when I have parallel light entering into this lens, it's going to diverge the light, which means that the focal point of this system is now going to be to the left of the lens. This is now going to be the focal point. And that makes sense because this is a negative correction. It's worn by myopes, and you should know that the far point of a myope is somewhere in front of their eye. All right. So now, what is this going to have? So I'm going to have a lens that's over here that's going to create a diverging wavefront. I'm going to take that spectacle lens and I want to convert that into a contact lens, right? I'm sliding in this direction. The magnitude of this diverging wavefront is going to be greater here than it is here. Therefore, I know that the contact lens correction, its magnitude has to be less than 7. All right. So when we do our problems, our answers must be less than 7. If it's not, we probably made a math error and we need to double check and go back over that. All right. So what we're going to do here, I'm going to now take this lens and I want to move it out here in space. This is my -7. This is my spectacle correction. Okay, and I'm sliding this guy out here. Now this is my contact lens correction. I want to know what that is there. All right, so I need to know the distance, the focal distance of this lens here. All right, and it's a 7 diopter lens. To find its focal distance, I'll just take the inverse of the 7. All right, and when I take the when I take the inverse of 7, I'm going to have 14.3 centimeters. So 0.143 is the distance from here to here. That is the focal distance of my -7 spectacle lenses. All right. Now I'm going to slide my contact lenses out here. The distance from here is going to be the vertex distance. That was 12 millimeters given to you on the problem. And now in this case, this focal point, in other words, this lens has to create a focal point aligning with the focal point of the spectacle lens. All right. So in this case, the focal distance of this lens has to be longer than the focal distance of this lens. So the focal distance of our contacts is longer than the focal distance of our spectacles. And so that is going to be from here to here. All right, so that's going to be the distance from here to here. That's going to be the focal distance of our spectacle lens correction. How are we going to find that? Well, I know that the distance from here to here is 143, and I know the distance from here to here is 12. And so I'm going to add those two together. And that's going to give me a 5, that's going to give me a 5, and that is going to give me a 1. So now I know that the focal distance, so this is 155. That is now the focal distance of my contact lenses. I want to turn that into a dioptric value, and that's going to give me the inverse of the 155. When I do that, that comes out to be a 645. I know it's going to be a minus. If mathematically you want to know why it's a minus, well, we're measuring from here to here. That's in a negative direction, so both of these values are technically going to have minus signs associated, which means that's going to have a minus sign, which means that's going to have a minus sign, which means that guy's going to have a minus sign. All right, we already know that that contact lens correction has to be less than the spectacle correction. 645 is definitely less than 7, so we got a half a shot that that answer is correct. All right, let's use the effectivity formula, all right, just to double check ourselves, all right? And so that's going to be our original spectacle correction, which is a -7, 1 minus the new vertex distance, which is 12 millimeters, times the original power of the specs, which was -7. All right, and then once again, we're moving from here to here, from spectacles to contacts with the path of light. This guy is now a positive value. All right, so now I have a positive times a minus. That gives me a minus. Minus a minus is a plus. That means our denominator is now going to be a number greater than 1, which means the answer has to be a number less than 7. Okay, everything should make sense. And when you do the math on that, that guy comes out to be 645 again. It's magic. And these two answers equate. Okay, easy enough. All right, one more for practice, and in this case, the value is going to be a whopping -12 diopters, and the vertex distance is given to you as 20 millimeters from here to here. So now I have a myopic correction. Its value is a -2. It's placed in front of the eye, and the distance from the eye to the spectacles is given to you as 20 millimeters. We're going from here to here. I'm going to take that spectacle correction, and I'm going to turn that into a contact lens correction here with a vertex distance of 0. And once again, I know that that answer here for the contact lens has to be a number less than 12, okay? Because I'm dealing with less divergent power. Therefore, this value to bring a object at optical infinity into focus, this value has to be less than 12. So I'm going to take my original spectacle correction, which is over here. That's a -12. That is going to give me a focal point somewhere back here. That's going to be the focal point that I want to equate for both the spectacles and the contact lens. I need to know the distance from here to here. That's a dioptric value. I'm going to take its inverse to turn it into a linear value. And excuse me, when I take its I take the inverse of the 12, and that's going to give me 0.083. So I know the distance between here and here is 0.83. All right, I'm going to move this lens over in this direction, okay, towards the eye or to the right. All right, this is my contact lens. This is my original spectacle location. All right, and I need to now know this guy here needs to create a focal point that is coincident with the focal point of the spectacle lenses. All right, so I need to know what the distance is from here to here. And to figure that out, I know, so the distance from here to here, I know the distance from here to here. That's the amount that I actually slid the lens, and that correlates to the vertex distance. So 20 millimeters from here to here. So I'm going to take my 0.083, and I'm going to add my 0.020 to that. And that fellow gives me a 3, and that gives me a 0, and that gives me a 1. All right, so this value right here is a 0.103, 10.3 centimeters. That is a linear value. I want to convert it into a dioptric value, so I'll take its inverse. That's the inverse of 103, and that gives me a value of 9.68. All right, 9.68 is a value less than 12. Makes sense. I got half a shot that that's the answer. All right, we'll double check ourselves, so to speak. You can actually do the effectivity formula first and then do the linear way second, however works for you. All right, but always have a way of double checking yourself. I want to know what the power of the contact lens is. That's going to be equated to the power of the spectacles, which is a minus 12. 1 minus the vertex distance. The vertex distance is 20 millimeters given to you on the problem. The value of the spectacles is, once again, 12. All right, I'm going from here to here. Specs to contacts with the path of light. That's going to give me the positive value here, which is going to be a numerator greater than, that's going to give me a denominator, that is greater than 1, all right, which is going to give me a value less than 12. And when you do the math for that, that's going to come out to be 968 once again. All right, so this guy and this guy are going to equate to each other. All right, so 2 ways of doing this problem. All right, this is understanding how the system works. Okay, this is a derivation of our Gaussian optics. All right, this one, people tend to prefer doing it this way because it's easier for them, but if you just memorize the formula, you're just cheating yourself. You need to understand why this fellow actually works, and understanding the differences in the focal distance is actually how you understand why these things work. Okay. The third part is going to be just the opposite. Now we're going to go from contact lenses to spectacles, and we'll come back to that in just a bit. All right, so we're back for the final section of this problem set, which is problem number 3. And now in this case, it's the opposite of problem number 2. You're giving a series of contact lens corrections, and they want you to convert them into spectacle corrections at 3 different vertex distances. Okay, and same thing. We're going to do the focal distance way, and then we'll use the Gaussian or the effectivity cheat. Okay, so the first problem is going to be a hyperopic correction, and that's going to be a pair of contact lenses that is a +5, and that's going to be a vertex distance of 0. All right, by definition, a contact lens. So here is our eye, here is our positive correction. It has a value of 5. Okay, and then we need to slide this fellow out into space at 3 different vertex distances. The first vertex distance is going to be 10 millimeters. The second vertex distance is going to be 16 millimeters, and the third vertex distance is going to be 20 millimeters. All right, this is a positive correction. All right, here's our positive lens. Going to have parallel light come into it, right? We're looking to look at an object at its optical infinity. It is going to create a converging wavefront, all right? And we're taking the power that is here and moving it in this direction in space, from here to here. You'll notice that the magnitude of the wavefront is less here. So we know that the spectacle correction here has to be less than 5. Whatever it is here, we know the spectacle correction at this vertex distance has to be less than this one. And then conversely, whatever this one is, this guy's got to be less than this one. So the value is going to decrease as we pass across or away from the eye. So a larger vertex distance. All right. So we're going to go back to our original lens, and that is going to be at a power of +5. And that is going to have a focal distance on this direction. Once again, hyperopic correction. I need a far point or a focal point that's going to be to the right or behind the plane of the retina. In any case, it's going to be to the right. And I know that this guy here, the distance from here to here, if this is a 5, I'm going to take the inverse of 5, and that gives me a value of 20 centimeters. So 20 centimeters from here to here. All right. Now I'm going to slide this guy out to this area here for our first problem. And that's going to be the distance from here to here is going to be 10 millimeters. All right, so this is going to be the location of our first spectacle lens. All right, so specs out here. And the vertex distance is going to be 10 millimeters. And I know that a parallel light comes through here. If these two equate, it's going to have to create a focal point at the same plane as the original one. So that the focal distance of this lens here is going to have to be from here to here. All right. And so to do that, I know that's going to be our 20 centimeter distance here, plus our 10 millimeter distance here. All right, we're going to add these two together. It's going to be this one plus this one. So that is going to be 210. That is going to be the focal distance, 210, of this spectacle lens here, and that's at a vertex distance of 10 millimeters. 0.210, I want to convert that back into a dioptric value, so I'm going to take its inverse, take the inverse of the 0.210, and that is going to give me a value of 476, and that's going to be positive. I'm measuring from here to here. That's going to be in a positive direction, so 426. And I know that 426 is less than 5, just what we speculated coming out here. I'm going to have to deal with less of a converging wavefront. All right, and the vertex distance for this guy is going to be my 10 millimeters. I'm going to do the same thing out here at 16, and I'm going to do the same thing out here at 20. All right, so I'm going to take my original focal length of the lens, which was the 20 centimeters, but in this case I'm now going to add the 16 millimeter vertex distance. That gives me a 6, a 1, and a 2. I'm going to take the inverse of the 0.216, and then for the final case it's going to be our original 20 centimeter vertex distance, but now, 20 centimeter focal distance, and the vertex distance is going to be 20 millimeters. That gives me a 0, a 2, and a 2. So 1 over 0.220. Converting linear values into dioptric values, do the math on those guys, and this comes out to be 436. It's going to be a positive. That's going to be at my 16 millimeter vertex distance, and this guy is going to come out to be a 455, and that's at the 20 centimeter vertex distance. Notice the values are getting smaller, 476, 436, 455. As we're going away from the plane of the eye, follows the rule. All right, so we got a half a shot of these answers being correct. All right, we're going to do the same thing. We're going to use our vertex formula. I'm going to start out with the power of the specs, which is going to be our original contact lens correction, which is the +5 divided by 1 minus the vertex distance, which is 10 millimeters times the +5. Now in this case we're going from here to here. I'm going against the path of light. That means that that vertex is going to have a negative sign associated. So I have a plus times a minus. That gives me a minus, a minus, minus a minus, a minus, minus, minus is a plus. So I know this value, this denominator, is going to be a value greater than 1, which means the answer here is going to be less than 5, less than 5. All right, and when you do the math, it comes out to be the same, 476. This value here and this value here are the same. Do it again for the next one. D specs, it's going to be the +5, 1 minus, in this case the vertex distance is going to be 16 millimeters, a minus here, a +5 here. Once again, we're going from here to here against the path of light. That is a minus. Work out the math on that, and that comes out to be a 463. Actually, that is wrong. I'm sorry, that's a 463 here. Sorry about that. Copied down the wrong number. 463 here and a 463 here, and then D specs over here, that's going to be our +5, and again 1 minus the vertex distance, in this case it's going to be 20 millimeters, minus sign, I'm going against the path of light, plus the 5, do the math on that, and that comes out to be the 455. Alright, so you'll notice that either way you do it, the answers come out to be the same. All right, so that is the first problem. That is for the +5. Now we're going to do it for the second associated value, and that is going to be a greater value, and that's going to be a +9. All right, and so +9 contact lens, and that's at a vertex distance of 0. All right, we're going to have our eye here. We're going to have our contact lens here. That is a +9, and I'm going to take that value and I'm going to slide it out in space once again to a distance of 10 millimeters. I'm going to slide it out to a distance of 16 millimeters, and I'm going to slide it out again to a distance of 20 millimeters. All right, so we'll do it the focal distance way first. I have a +9 lens over here, parallel light coming into the systems, going to cause a focal point that is over here in space to the right. All right, I need to know the distance of that focal point, or the focal distance of this lens, depending on how you want to look at it. And I'm going to take the inverse of the 9. Excuse me. When I take the inverse of the 9, and that is going to give me a 0.111. Okay, so the distance from here is 0.111 from here to here. Now I'm going to take that plus lens, I'm going to slide it out in space this way, and the distance from here to here is going to be our new vertex distance of the glasses, which is going to be 10 millimeters, and that's the value that we're looking for here. All right. So now this focal distance, light coming in, has to form a focal point in the same position right here again. So now I need to know the distance from here to here, and I'm going to do that by taking my 0.111 and adding my vertex, which is my 0, 1, 0, and that gives me a 1, a 2, and a 1. All right, that is the focal distance of my new contact, or my spectacle lens, excuse me, at a 10 millimeter vertex. I'm going to take the inverse of that 0.121, and when I do that, that gives me a value of 836. Okay, once again, I'm measuring from here to here. That gives me a positive here, gives me a positive here, and that is at a vertex distance of 10 millimeters. All right, 836 is less than 9, so we got a half a shot at that being correct. Going to do the same thing out here at 16, and then out here again at 16, and then out here again at 20. All right, so I'm going to take our original value of the 111, that's the focal distance of our original lens, and I'm going to add the vertex for the second, which is 16, take the 111, add the vertex for the third, which is going to be the 20 millimeters. Okay, this is going to be a 7, this is going to be a 2, this is going to be a 1, this guy here is going to be a 1, a 3, and a 1. I'm going to take the inverse of those fellas to give me a dioptric value. So the inverse of the 127, I'm going to take the inverse of the 131. All right. The inverse of 127 comes out to be 787. And so that's going to be our spectacle lens power at a vertex distance of 16 millimeters. Take the inverse of the 131, and that gives me a 763, and that's at a vertex distance of 20 millimeters. All right. Once again, the 836 is less than the 9, and the 787 is less than the 36, and the 763 is less than the 787. So it's following the patterns that we should have, and so we got a half a shot at this being correct. We're going to use the Gaussian formula to do it again. So I'm going to start out, I want the power of the specs. To do that, I'm going to start out with the original contact lens, which is going to be a +1, 1 minus. My first vertex distance is the 10 millimeters times the power of the lens, which is a 9. I'm going from here to here. I'm going against the path of light. That's going to be a minus value. This is a plus times a minus. That gives me a minus. If I minus a minus, that gives me a plus. So my denominator is once again going to be greater than 1, which means my answer is going to be less than 9. Okay? And when you do the math for that, this guy comes out to be an 826. It's going to be a plus 826. This guy is going to be D specs over here. That's going to be the +9, 1 minus. Vertex distance here is 16. Also going to the left, minus sign, +9. Do the math on that. That guy comes out to be a 787. And then do it again. power of the specs. Original contact lens is a 9, 1 minus. This vertex distance is a 20 minus. I'm going against the path of light, and my 9 again, do that guy, and he comes out to be a 762. All right, and so you'll notice that these guys, I'm a decimal point off here or there. No big shake. All right, this guy 720. This is a 726. I'm sorry. This guy actually came out to be correct. He is the same here. This guy here is the same here. This guy here is off by 1/100th of a diopter. Why is that? All right, you're going to notice this as you're rounding off. You're going to have some sort of changes in the rounding off, especially when you're dealing with these higher powered lenses. Okay, but not something that's going to give you a problem or give you an answer that'll be wrong on the test. They're never going to be that close. They're going to be in the same range. Okay, so you don't have to worry about that. But your answers are going to be pretty much the same. Dealing with lower powers, they'll be exactly the same. When you're dealing with higher powers, 9, that's a pretty high prescription. You're going to notice that you might be off by a decimal place or so. Not a big shake. Not a decimal place, but a unit, usually in the hundredths over here. So not a big shake. All right, so that is for the 9. And then we have another one, which is the 5. All right, so we're going to take the +5, and that +5 is going to be a contact lens, and that's at a vertex distance of 0. I have an eye over here. I have a contact lens over here, which is a +5, and then I'm going to slide them out to make them into glasses at a vertex distance of 10 millimeters, slide it out again for a vertex distance of 16, and then slide it out again for a vertex distance of 20. All right. Once again, I'm going to take my lens. I'm going to have parallel light entering that lens. That lens has a power of 5. It's going to cause a focal point that is going to be 1/5. All right, that's where our far point is going to be over here. So the distance from here to here is going to be 20 centimeters from here to here. Now I'm going to move this off the plane of the eye, slide it out in the space here, and for the first vertex distance is going to be 10 millimeters from here to here. But if that spectacle correction works or is equivalent to the contact lens correction, it will also need to form a focal point at the same point. And so the focal point of the spectacle lens, therefore, will be from here to here. All right, this 1/5, that's 20. Okay, so I'm going to take my original focal distance of the contacts, which was the 20 centimeters, and then I'm going to add my vertex distance, which is 10 millimeters. That gives me a 0, that gives me a 1, that gives me a 2. All right, that is the focal distance of the first spectacle lens at a vertex distance of 10 millimeters. I'm going to take the inverse of that 21 centimeters, and that's going to give me a value of 476. All right, and that's going to be at 10 millimeters. All right, once again, this is the 5. We're moving it out in space. All right, so I have a converging wavefront. I'm going from here to here, less converging power here than here. So I know the spectacle lens at this point has to be less than 5. Whatever it is here has to be less than here. Whatever it is here has to be less than here and here and here. So the value should be decreasing as we're sliding away this way. All right, we're going to do that again for 16 millimeter vertex distance, and we're going to do it again for our 20 millimeter vertex distance. So we'll start out with our original focal distance and then add now in the 16 millimeter vertex distance, start out with our original focal distance, and then add in our 20 millimeter vertex distance. That gives me a 6, that gives me a 1, that gives me a 2. This one is 0, that's a 2, and that's a 2. And then these are linear values. I want to convert them into dioptric values. I'll take the inverse of the 216. When I do that, that gives me a 463, and that's going to be at a vertex distance of 16 millimeters. I'm going to take the inverse of the 22 centimeters, and that's going to give me a 455, and that's going to be at 20 centimeters. All right, 476 is less than 5, 463 is less than 476, 455 is less than 463. The world is a wonderful place. All right, let's do it with the Gaussian. I want to know what the specs are going to be. I have to start out with my original contact lens correction. 1 minus my vertex distance is going to be 10 millimeters times the original power, which is the +5. I'm going from here to here. I'm going against the path of light. Therefore, this has to be a minus value. That's a plus times a minus. That gives me a minus. I'm minusing a minus, which gives me a denominator greater than 1, which means my answer will be less than 5. When I do the math for that, that comes out to be 476. All right, 476 here, 476 there. Magic. D specs over here. This is going to be the +5 over here. 1 minus the vertex distance here is 16 millimeters. Once again, I'm going to the left. That has a minus sign associated with it, times the +5. Do the math for that. That comes out to be a 463, 463, 463. D specs over here. That's going to be the +5. 1 minus the 0.020. That's my third vertex distance. Going to have a minus sign associated with that guy also. Do the math for that, and he comes out to be 455. 455 here, 455 here. Notice that the numbers, even to the second decimal point, are going to be the same either way. All right, and then once again, that's because we're dealing with a value of +5, which is not a unreasonable correction. All right, that guy without his glasses is pretty blind compared to this guy who's blind as a bat without his glasses, the +9. And you'll notice that our figures kind of dribble off here depending on how you want to round these values off here. All right, but once again, that's not going to screw you up on a test. Don't worry about that. What you're dealing with is the patterns that you need to know, and you're never going to have two answers that are off by 1/100th of a diopter that's going to cause you to break you one way or the other. All right, and so that is all of the problems for this week. If you have any questions on that, post your questions to the discussion board, and we'll see you next week again. All right, so we're back again, and we're here doing the last set of problems, problem number 3, but the last 2 items. And in this case, we're now dealing with a myopic correction. So we're giving a contact lens that is a -8, and that's at a vertex distance of 0. So I have my eyeball here, and I have a minus contact lens sitting on the surface of the eye. And then once again, they're asking you to put it into, they want to know the value of the spectacle correction, and that's going to be at 3 separate vertex distances. One is going to be the 10 millimeter vertex distance, 16 millimeter vertex distance, and a 20 millimeter vertex distance. All right, so I'm going to go back over here. I have a minus lens. It has a magnitude of 8. It's going to take parallel light coming in and cause it to diverge. So I'm going to create a focal point that is in front of the lens. And that focal point should correspond to the far point of the patient. In other words, they're myopic. They should have a far point that is in front of them, in front of their eyes. Remember, myopes can at least see something. All right, and I need to know where that focal point is. That's relatively easy. I'm going to take the inverse of the 8. And that's going to give me 125. So I know the distance between here and here. Let's do it here, 1.125. And so 12.5 centimeters from here to here. All right, now I'm going to put a pair of spectacle lenses out here in space. And that vertex distance to begin with is going to be 10 millimeters. So from here to here, that is 10 millimeters. Now, for these pair of spectacle lenses to work the same way these contact lenses worked, that this lens is going to have to create an image that corresponds at the same focal point as the contact lens. Therefore, the focal distance of this lens is going to be from here to here. This is the value that I'm looking for here. How am I going to find that? Well, it's going to be this focal length less the vertex distance. So I'm going to take the 0.125 and I'm going to subtract the 10 millimeter vertex distance from that, and that gives me a 0.115. So the value here is 0.115. Right? That is the focal length of this spectacle lens at a 10 millimeter vertex distance. If I want to know what its dioptric power is, I just take its inverse. So I take the inverse of the 0.115, do the math on that, and that comes out to be 870. All right, so I'm measuring from here to here. That's against the path of light, therefore this has a minus value, and this also has a minus value. Okay, so same thing, we're trying to figure out what the power of these spectacle lenses is. All right, and so we're going to have a diverging wavefront from our negative value. Our focal point is going to be here. The magnitude of this wavefront is going to be greater here than it is here. So as I put spectacle lenses farther and farther out into space, they're going to have to handle a greater amount of vergence than the contact lenses. Therefore, the spectacle lenses should always be greater than the contact lenses, and 870 is definitely greater than 80. All right, and so this is going to be at a vertex distance of 10 millimeters. All right, we're going to do the same thing for the next pair, and that this vertex distance from here to here is now going to be 16, and then we'll do it again for 18. So I'm going to take our original focal distance of our 8 diopter contact lens, and in this case I'm going to subtract my 16 millimeter vertex distance. Then I'm going to do that again, and I'm going to subtract my 20 millimeter vertex distance. This guy, when you do the math, comes out to be 109. I'm going to take the inverse of the 109. Once again, I'm measuring from here to here against the path of light. Do the math on that, and that comes out to be a minus 917, and that is at a 16 millimeter vertex distance. Once again, we're farther out in space, therefore this has to handle more power. This value should be greater than this value. Take your 125, subtract your 20 from that, and that gives you 105. Going to put that over here. That's my focal distance of my final spectacle lens configuration. Has a minus sign associated with it. Do the math on that, and that comes out to be 952, and that's going to be at a vertex distance of 20 millimeters. All right, so once again, I have my 8, then to an 8.7, then to a 9.17, and then to a 9.52. It makes sense. These values should be getting larger. I'm going to double check myself with my effectivity formula. So I'm going to do the power of the specs. That's going to be the original contact lens, which is 8 diopters, 1 minus. The first vertex distance was 10 millimeters. I'm going from here to here against the path of light. Therefore, this is going to have a negative value associated with it, and then times the original minus 8. So a minus times a minus is a plus, and so this is 1 minus something. So this denominator is going to be less than 1, which means the value here is going to be greater than 8. That makes sense. And if you do the math, it comes out to be 870. All right, so this value here is going to correlate to this value here. All right, D specs for the second set. It's going to start out with our original contact lens, a minus 8. 1 minus the new vertex distance is 16 millimeters here. Once again, I'm going from here to here against the path of light times the minus 8. Do the math on that, then it comes out to be, oh, look at that, 917. All right, so this value and this value correlate together. And then for the final one, we'll do the D specs. That's going to be a minus 8 again. 1 minus our vertex distance here is now going to be 20 millimeters to the left against the path of light, minus sign associated with it. The original power, which was minus 8. Do the math on that one, and it comes out to be 952. All right, so this value correlates to this value here. All right, so once again, you can do it by the focal lengths, you can do it by the effectivity formula. All right, if you understand the focal lengths and how to do the focal length, you understand the concept of the problem, and that is what you're trying to accomplish here. You're understanding, not just getting the answer. All right. All right, now for the last one that we're going to do, the power is still going to be a myopic correction, but it's going to be that much more power. We're now dealing with a minus 11 lens, and that's going to be a contact lens, so it's going to have a vertex distance of 0. So I'm going to have my eyeball here, I'm going to have a minus 11 lens here, and then I'm going to turn this into spectacle lenses. All right, so I'm going to have a vertex distance of 10 millimeters, 0.010. Then I'm going to have another pair of spectacles out here, going to lengthen it to 16, and then ultimately I want to lengthen it to 20 millimeter vertex distance. We're going to need to determine what the powers are out here. Once again, I'm moving away, I'm moving against the path of light. I'm moving closer to the point of origin of this divergent wavefront. So these values need to be increasing in power. In other words, this one needs to be more than 11, this one needs to be more than this, and this one needs to be more than this. All right, so how we're going to do that? By our focal lengths. Start out with my original lens, that's a minus 11 lens. It is going to cause a focal point in front of the lens out here. If that is the patient's correction, then that focal point there will correspond to the far point of the patient's eye. Once again, myops, focal point in front of their eye. Now I want to take this and I'm going to put them into a pair of spectacle lenses, and the distance from here to here is going to be my 10 millimeters. I need to know what the focal distance of this lens is. That's going to be from here to here. Here's my vertex. So find from here to here. I'm going to take the 11 diopters and take its inverse, and that comes out to be 0.091. All right, so this is 0.091 here. For this spectacle lens at a vertex distance of 10, its corresponding focal point needs to be in the same position as this one. So I need to know the focal distance of this lens here, and that will be the distance from here to here, which is going to be our 0.091 minus our 0.010. Do the math on that, and comes out to be 0.081. All right, so that is the focal length here, 0.081, from here to here. That's a focal length. I want to convert that into a dioptric power, so I will take its inverse. All right, when I take its inverse, it's going to come out to be 1235. I'm measuring from here to here against the path of light. That's going to give me a negative value here. That's going to be a negative value here. All right, and that's going to be at a vertex distance of 10 millimeters. We know that the answer has to be greater than 11, and it turns out to be 1235. We got half a shot there. Going to do the same for the 16 and the 20 vertex distance. Start out with our original focal distance of our 11 diopter contact lens. We're going to subtract the 16 diopter vertex distance. That comes out to be 0.075. That's our focal length. I'm going to take the inverse of that focal length to determine our dioptric power. Once again, that has a negative value associated with it, and this comes out to be a negative 13.33 diopters. That's going to be at a vertex distance of 16 millimeters. 13.33 is greater than 1235, which is greater than 11. All right, follows the pattern. For our last one, that's going to be the 091, the original focal distance of the 11, minus the vertex distance of 20 millimeters, and that's going to come out to be 0.071. All right, that's the focal distance of our final lens configuration, and that's going to have a minus sign, once again measuring from right to left. And so 0.071, do the math for that. That comes out to be 1488. All right, and that's going to be at a 20 millimeter vertex distance. And you'll notice how these are increasing. They're increasing relatively large amounts, 12, 13, 14, almost diopter changes, diopter and a half change, and that is because of this massive magnitude. Once again, divergence is not a linear function, and so the change is going to increase as the vertex distance gets larger, so a non-linear change in power. Going to double check yourself with your vertex formula. Power of the specs is going to be the original power of the contacts, 1 minus the vertex distance, 10 millimeters to start, going from here to here, contacts to specs, against the path of light, minus sign there, on the vertex times the original 11. This comes out to be 1236. Okay, 1236, 1235, that's pretty darn close. All right, so that's just a rounding error, and that is because of the large magnitude. All right, but you're going to be, within 1/100th of a diopter. Can't beat that with a stick. All right, so specs for the second one, using the vertex formula or the effectivity formula or the Gaussian cheat, however you want to call it. Our next vertex distance is 16 millimeters. Also going to have a negative sign associated with it. Negative sign over here. All right, minus times a minus is a plus. 1 minus a plus. Smaller number here, which is going to give you a value here larger than 11. And this comes out to be 1335 on your calculator. Once again, that's pretty darn close. All right, and same rounding error that we spoke of before. But certainly, you're not going to get tripped up on an answer on a problem on a test with this kind of change here. They're never going to be that close, all right? But the values are going to be the same. So you can come to your conclusions either way. All right. This way is more of a cheat. This way, people tend to prefer it this way because you like to chug and plug on formulas, but actually understanding why those changes are and how the focal points of the contact lens and the specs have to equate to itself is actually understanding how the optics actually works. All right, for our final one here, that is a 20 millimeter vertex distance subtracted here, or have a negative sign there, 11 diopters here. Do the math on that, and that comes out to be 1410. That's not 1488, that's 08. And then this guy comes out to be 1410. All right, and then once again, that's within 2/10. That's pretty close. All right, so that is the final problem for this problem set. You should understand both ways of doing this. Okay, you should understand why a myope's contact lens correction is greater than their spectacle correction, and then conversely, why a hyperope's contact lens correction should be more than their spectacle lens correction, and why those things work. All right, the Gaussian portion of this we're going to get to when we get to Gaussian optics. Okay, and then understand the juxtaposition of power of the lens or the SSRS of a model eye and the axial length and how they're going to work. All right, if you have any questions on any of that stuff, please post them to the discussion board. And other than that, we'll see you back next week.